Moving thousands of tons of steel across the country in a heavy storm requires split-second coordination. Track switches, crew schedules, and passenger tickets all have to align perfectly, in real time, across a nationwide grid. To manage that massive logistical puzzle, America's National Passenger Rail relies on an architecture that was originally designed in 1981. That system is called Aero. If you look at a mainframe terminal from that era, it is easy to assume the technology is broken. But it isn't. Aero successfully processes a national reservation workload every single day. Keeping a system running reliably through 4 decades of shifting travel patterns, new ticketing channels, and changing passenger expectations is a genuine engineering achievement. The code does exactly what it was built to do. But that extreme day-to-day reliability has created a trap. Because Aero rarely fails, leadership has had little short-term incentive to replace it. Over 40 years, that delayed action has allowed technical debt to quietly compound. Today's passengers expect mobile-first booking, instant itinerary updates, and biometric boarding. A transaction processor built in the early 80s cannot natively support those functions without heavy middleware. Maintaining the current architecture requires engineers fluent in IBM Macro Assembler. As the specialists trained in those early languages age out of the workforce, the institutional knowledge required to keep the system running is shrinking, creating massive key person risk. To keep up with modern demands, developers have spent decades bolting point-to-point integrations onto the core. The logic is now so tightly coupled that adding even a modest new feature requires long, fragile development and testing cycles. This forces executives managing aging infrastructure into a difficult choice. Do you keep paying to maintain the dinosaur, execute a basic cloud migration, or risk a full AI-native rebuild? A system can be highly reliable without being extensible. As a software architecture ages, the gap between those two properties widens, forcing leadership to choose one of 3 distinct modernization paths. This matrix compares the 3 paths forward, mapping options against transition risk, maintenance costs, feature velocity, and AI readiness. Option 1 is the status quo, maintaining the 1981 mainframe architecture. This carries 0 transition risk, but drops feature velocity to dead last. You gain short-term stability, but forfeit the ability to support dynamic pricing. Meanwhile, maintenance costs continue to rise. Option 2 is a lift-and-shift cloud migration. This transfers legacy code off the physical mainframe and onto modern cloud servers. This path removes the physical burden of managing your own data centers. It gives you infrastructure elasticity and vastly improves your disaster recovery, but it largely preserves the legacy application logic. The underlying constraints simply move to the cloud, which prevents native AI integration. Both the status quo and the cloud migration prioritize short-term safety over long-term capability. Taking either of these routes guarantees that a second, much harder modernization effort will be required later to actually upgrade the operations. Option 3 is the Titan ACRS proposal. This is a purpose-built, cloud-native architecture designed from first principles, rather than migrated legacy code. This chart breaks down the new architecture. Instead of a single monolithic core, ACRS uses microservices. It organizes operations into 4 independently deployable layers, building upward from physical edge safety to the passenger experience. At the physical edge, this architecture enables hardware like Titan BioGate. Enrolled passengers can walk right up to the platform and board using sub-second facial verification, eliminating paper tickets and queue delays. Deploying biometric boarding requires strict operational controls. All passenger profiles must be stored as encrypted mathematical templates. Enrollment has to be strictly opt-in, and parallel physical ticketing systems must remain operational for those who decline. Moving up the stack to the cognitive layer, the platform includes the Victoria Conversational AI. This interface is designed specifically for non-technical executives and station staff to interact with the system. Instead of hunting through reporting software, leadership can type a plain text question about today's regional revenue or station delays, and Victoria instantly converts the raw operational data into a polished visual summary. A conversational assistant only works if the unified API layer beneath it is perfectly integrated. Without clean, centralized data, the chatbot will just return errors. By embedding predictive models into the core, The network shifts toward a system where demand forecasting and maintenance alerts arrive in seconds rather than days. Total system replacements carry a notorious reputation in enterprise IT. Attempting to swap out the backbone of a national rail network at once has a high probability of turning into a massive, multi-million-dollar failure. To mitigate that, the Titan proposal actively rejects the traditional $250 million enterprise-wide cutover. This diagram illustrates their alternative path. Phase 1 limits the initial proof of concept strictly to a single station for 3 to 6 months. The sole purpose is to validate the technology in the real world before committing further capital. This approach contains the blast radius of a potential failure. If the system doesn't perform at one station, the organization has only risked a modest discovery budget. Funding for Phase 2 and 3 is completely contingent on the success of the prior stage. The trade-off for this caution is time. Slicing the deployment into independent, trackable stages deliberately stretches the enterprise modernization timeline out to as long as 36 months. The ACRS proposal relies on a phased rollout strategy that identifies technical flaws early, before any nationwide capital is committed. This dilemma extends far beyond passenger railways. Any organization managing aging physical infrastructure eventually hits this exact modernization wall. This decision tree maps the approach. Organizations with static processes and strict mandates to avoid transition risk follow Path A, a lift and shift migration. Leaders recognizing predictive maintenance and real-time operations as the new baseline follow Path B, an AI-native rebuild. Choosing to maintain a legacy system is still a choice, and eventually, the financial burden of patching old code and retaining specialized talent will eclipse the cost of simply building a modern platform. Escaping the mainframe trap requires a modular rebuild that proves its financial and operational value one phase and one station at a time.